Review video number 10, freefall graphs with and without air resistance. Here we compare the motion of objects that are not experiencing friction or air resistance, which, by the way, is friction with the air, with objects that are. An object of mass m dropped from rest at an elevation near Earth's surface where the acceleration due to gravity is g. Draw graphs below using the following criteria. Assume that the initial position will be y equals 0, with the y values becoming more negative with time. Where possible, designate known values along a vertical axis, such as the values of asymptotes. If a slope is 0, draw an arrow pointing to that region and write slope equals 0. If the slope is non-zero but constant, and we know what its value is, draw an almost triangle. A rise over run thing, basically an L in that region, and write the slope's value. All right, let's get to it. What we have on the left is when there's no air resistance, and on the right when there is. When there is no air resistance, and we don't have to do these in order necessarily, we can do them in whatever order we want. How about if there's no air resistance? This graph in the lower left with acceleration, won't there be that constant acceleration if there's no air resistance? And you know what, while we're at it, since we've drawn that one already, if there's no air resistance and we're dropping something from rest, then isn't its velocity going to change at a constant rate, where that slope right there is g? Where if there's no air resistance, what does that mean with regard to our position? With position, that means we're going to end up with some kind of a parabolic thing like that. What if there is air resistance? If there is air resistance, why don't we start with acceleration again? If there is air resistance, then the initial acceleration will be equal to g, but then as it falls, presumably it won't hit the ground before this happens, it will reach terminal velocity. And when it reaches terminal velocity, its acceleration has a value of 0. So that means that it's likely to have a curve that looks kind of like that. What's going to happen with the velocity? The velocity, it's going to reach a terminal velocity. It's going to reach some speed where it's not going to speed up anymore. Negative is in the downward direction. So we could call that the terminal speed right there, that asymptote. And what's going to happen to the position? Well, the position is going to start, it's going to curve kind of like it did at the beginning, but then at some point, the velocity is constant. And so at some point, if the velocity is constant, then won't this position curve go linear? Know what I mean? Kind of like that. Where that slope right there, that's VT right there. That's your slope. Last thing for this video. Previously, we solved a differential equation for the case of part B. Along our way, a natural logarithm appeared. Almost always we use absolute value symbols anytime we have a natural logarithm. That is, instead of writing natural log of v, we might write natural log of the absolute value of v. Now, why is that? In other words, what is true about logarithms that would cause us to usually write the log of v? Well, you can't take the logarithm of a negative number.